In the last video, we talked about how the wave-like properties of electrons explain the bonding patterns of molecules. We also talked about hybridization and how it can explain the bonding properties of carbon. The only concept left to conclude it is how atomic orbitals act in 3D space to form molecular orbitals. Before we talk about how the orbitals interact with one another, we should probably mention how they look. I'll demonstrate this concept using balloons. The center where my fingers touch is a carbon's nucleus. The balloons I'm holding will each describe one of the orbitals, but in general, keep in mind that they represent an electron density region. The s orbital we discussed in the last video looks like a sphere, pointing out sideways. The p orbital we discussed in the last video looks like a dumbbell, the same one you might do bicep curls with, pointing up and down over the carbon center. Now we can discuss how these orbitals interact with other carbon orbitals. For that, we'll use more balloons. Let's say that we have a single bond between one carbon and another carbon. We're going to ignore everything else going on in this molecule and focus solely on the single bond. We can know how the two carbon atomic orbitals fused to form the single bond. What we know is that the bond was formed by the two s orbitals of the carbon smashing into each other due to their shape. We call this type of bond a sigma bond. Therefore, we say that sigma bonds are a result of head-on interactions between s orbitals. But let's take, for example, a double bond. One of those bonds is formed by the same head-on interaction that happens in a single bond. But what happened with the second bond? When the second bond forms, one of the two parallel p orbitals on each carbon touch each other and form what is called a pi bond. Therefore, we say that pi bonds are a result of the side-by-side interaction between p orbitals. A similar thing happens with triple bonds. One of those bonds was the sigma bond formed by the first bond, and the second was a pi bond formed by the second bond. Remember that we have two, not one oval on each carbon. So, the third bond will be formed by the side-by-side interactions of the other p orbitals. The next thing I say is usually not tested this early in the course, but becomes an important concept in the later chapters. Notice that a single bond between two carbons can rotate freely. We have a very special term for this. Single carbon-carbon bonds exhibit free rotation, or the ability to freely rotate around one another without breaking. This doesn't hold for double or triple bonds. If I try to rotate a double bond, at least one of the two will break. The same goes for a triple bond. If you need to remember this on a test, I like to teach a trick with your fists. Sigma bonds are formed by a fist bump. A double bond is formed by your thumbs touching, and a triple bond is formed with your pinkies touching. In summary, a single bond between carbons consists of one sigma bond, a double bond between carbons consists of one sigma bond and one pi bond, and a triple bond consists of one sigma bond and two pi bonds. I want to summarize the past couple videos with one big practice question. This molecule is Lipitor, a drug used to treat high cholesterol. Take some time to answer these questions. How many sp3 hybridized carbons are there? How many sp2 hybridized carbons are there? How many sp hybridized carbons are there? How many carbon-carbon sigma bonds are there? How many carbon-carbon pi bonds are there? Pause the video to do the problems. Hopefully you've taken some time to answer the questions. I'll go ahead and go through them one by one. There are 9 sp3 hybridized carbons, labeled in blue. There are 24 sp2 hybridized carbons, labeled in red. There are no sp hybridized carbons. There are 33 sigma bonds, labeled in red, and 11 pi bonds, labeled in green. As always, there will be practice sheets and explainer videos linked for this chapter in the description. In the next video, we'll move on to the final video of Unit 1, where we'll discuss our current understanding of the 3D structure of molecules.